Hello, this is Jack Jackson. In the last playlist, we looked at quadrilaterals. We started talking about classifying them, and then we started looking at some subclasses of quadrilaterals. Particularly, we spent quite a bit of time talking about kites and their properties. And remember, kites were, among other things, they were a quadrilateral where you had the major diagonal uh, split it into two congruent triangles with a reflection. In this chapter, we're going to be continuing our study of types of quadrilaterals, so this playlist will still be about that. A major focus will be studying the properties of the types of trapezoids, including parallelograms, isosceles trapezoids, rhombi, rectangles, and squares. And since these shapes all have at least one pair of parallel sides, it's time for us to more formally study a few critical results about parallel lines. So first of all, let's remember our definitions. Two lines are parallel if and only if they are coplanar and non-intersecting. Two subsets of lines, like line segments or rays, are said to be parallel if and only if the lines containing them are parallel. Two lines in different planes are skew lines. Skew lines also do not intersect. So here's the question. Given a line L and a point P not on line L, how many lines go through P that are parallel to L? Okay, now we've actually investigated this earlier in the course. This turns out to be a critical question when it comes to the study of Euclidean geometry. And in particular, the study of this question led to the development of hyperbolic geometry and the idea that we could have these multiple geometries that we've been studying. So we want to see what the answer to this question is. And we've actually already seen this. In spherical, the answer is 0. In Euclidean taxicab geometries, exactly 1. In hyperbolic geometry, infinitely many. And since they are all inconsistent with each other, and all four of these geometries satisfy all the postulates before the SAS postulate, and Euclidean hyperbolic and spherical geometries satisfy each of the postulates thus far, including the SAS postulate, we see that we need one of the following postulates to narrow the geometry down to exactly one of Euclidean hyperbolic or spherical geometry. Therefore, which of these we choose to accept will give us a postulate that is independent of the other postulates, and accepting it will eliminate the other two geometries. So here are three different versions of a parallel postulate. For Euclidean and taxicab geometries, we have the Euclidean parallel postulate. Given a line L and a point P on that line, there exists exactly one line through the point P parallel to the given line L. That's our normal Euclidean parallel postulate. In hyperbolic geometry, we'd have to change it to say, given a line L and a point P not a line, there exist infinitely many lines through the point P parallel to the given line. And in spherical geometry, our parallel postulate would say, given a line L and a point P not a line, there exists 0 lines through the point, or no lines through the point P parallel to the given line. So remember, in spherical geometry, parallel lines do not exist. Any pair of distinct lines in the same plane must intersect in exactly 2 points, which those intersection points are an antipodal pair, like the North Pole and South Pole on Earth. So this version of the Euclidean postulate right here is often known by the name Playfair version because it was given in a book by Playfair, uh, Englishman from 1795. However, Playfair didn't come up with this. It was known way before that. It was known to be equivalent to Euclid's fifth postulate at least as early as the 5th century. Definitely we know that Proclus knew of this back that far. So this postulate the version of the postulate goes way back, way farther than Playfair, but you'll hear this referred to as the Playfair version. So here are some illustrations. In Euclidean geometry and taxicab, there's exactly one parallel. In spherical geometry, there are no lines parallel. So if you look here, you take a line here and a line here. No matter where you place these, they're going to intersect in a pair of antipodal points. Here, if you start with the line here in Euclidean geometry, take a point not on it, there's exactly one line parallel to that. But look at the situation here in hyperbolic geometry. Here we have a line, this darker line here, and then we have a point over here, and all of these red lines here go through that point, and they do not intersect this line. They're in the same plane. Even this line right here, where they sort of intersect at infinity, they intersect at a point. These as Euclidean objects, these semicircles intersect at a point on the hyperbolic plane edge. But remember, those points are not actually in the geometry, so they're not really part of either line. So those don't even intersect either. And all these others don't either, include this vertical line, these other lines here. And so you can see, I think you can imagine that you can draw many, many, many of those, infinitely many, in fact. Now, uh, this discovery was a really remarkable fact, and a lot of people tried to prove Euclid's fifth postulate, or the Proclus version, Playfair version of the parallel postulate, like we're saying here. And they could eliminate the spherical geometry because spherical geometry um, is has some other problems. Like if you remember, we had to modify some of our postulates earlier to allow spherical geometry to happen. But they keep trying to prove this thing that there couldn't be more than one, or ultimately infinitely many, parallel lines through the point, not on a line. And of course, now we know by the existence of hyperbolic geometry, there's no way to prove that. It has to be taken as a postulate. But many, many mathematicians worked on that. Now, we've been taking the viewpoint all along, all semester, that Euclidean, taxicab, hyperbolic, and spherical geometries are taken on an equal footing, with each being an equally legitimate geometry. Yeah, maybe with Euclidean geometry being our preferred one, but not necessarily always. And there's really no inherent preference for any of the four geometries up to this point in our formal study. Postulates are viewed as sets of statements which are accepted as true, and they establish a geometric playground in which we can work, make conjectures, and prove propositions. So the purposes of formal study of abstract geometries, we don't really care if they accurately portray the real world or not. However, ultimately, each of these four geometries do model certain real-world environments, making them even more worthy of study as practical systems for applications. Certainly, we've been using Euclidean geometry well for modeling moving around a flat surface. Taxicab makes more sense when we're restricted movements along perpendicular streets and avenues. Spherical geometry is more useful in describing movements about the surface of the Earth. And hyperbolic geometry has even been used to help explain some of the behavior of the universe on a more cosmic scale. So even though each of these geometries is ultimately practical, for the purposes of this course, it's entirely secondary that they have practical applications to real-world phenomena and that they can be used to solve practical problems. The important thing for us is the intellectual exercise of determining the consequence of accepting a particular set of postulates. However, this approach and viewpoint have definitely not always been the way mathematicians have thought about geometry. In the most ancient times and in many cultures around the world, the study of geometry and mathematics in general was focused on creating tools for solving practical everyday problems. Ancient civilizations in Egypt, Babylon, India, China, and many other places all made significant discoveries and applications of geometry. After the ancient Greeks, from Thales through Euclid and on through Archimedes to Hypatia, lifted the study of geometry, rigorous exercise, and pure logic, the study of geometry became a central focus of mathematical thought and expansion for hundreds of years. In fact, geometry was really the center of mathematics for many, many, many centuries. To the credit of Euclid, which was, of course, based on his work on some of his predecessors' work, he realized that we must take some statements on faith as postulates, and that once we did that, we can then use them to prove propositions as a result. You can find a list of postulates in the first section of these notes, or in our earlier first section of the videos in the first playlist here on geometry of his postulates. Euclid's way of looking at these postulates was they were obvious statements of how the real world was put together, or at least an idealized version of it. So for many centuries, it never occurred to anyone that there could be any set of reasonable postulates for any geometry that result in something different from Euclidean geometry. No one ever considered that the postulates of Euclid might be false in some context. However, one of Euclid's postulates seemed to be much more complicated than the rest. It was this fifth postulate. If two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than two right angles, then the two lines inevitably must intersect each other on that side if extended far enough. Well, first of all, it's much more wordy, a little more complicated than the way he phrased his other postulates. We now know that it's logically equivalent to the Playfair version of the Euclidean postulate that we just talked about. So proving these two statements as logically equivalent means if we accept either one of them as a postulate, then we can prove the other one as a proposition. Of course, we're assuming that we've accepted the earlier postulates. So it bothered mathematicians that Euclid's postulate was more complicated than the other postulates, and apparently bothered Euclid as well. Euclid took pains to prove as much as he could without using his fifth postulate, even when an easier proof existed using it. Only when he exhausted all these results did he resort to utilizing the fifth or parallel postulates. And many mathematicians felt that one should be able to prove the fifth postulate as a consequence of the other postulates and propositions. Now, if they'd been able to do this, then they would have shown that it was dependent on the other postulates, making it a proposition. Of course, with hindsight and the benefit of knowledge of later discoveries, we know that this was an impossible task. In particular, the existence of hyperbolic geometry and Euclidean geometry tells us that the parallel postulate is independent of the other postulates, and any attempt at proving it from the other postulates was doomed to failure. Of course, prior to the discovery of hyperbolic geometry, mathematicians had no idea that this was true. In fact, they could not conceive of a geometry different from Euclidean geometry. Many very good mathematicians set out to prove the fifth postulate as a consequence of the earlier postulates and propositions. Notable attempts were made by Ptolemy, who lived from 85 to 165, Proclus, who we'd mentioned earlier, from 411 to 485, Wallis, from 1616 to 1703, and two mathematicians, Sacchieri, from 1667 to 1733 was his lifespan, and Lambert from 1728 to 1777 was his lifespan. Those two particularly came close to developing the idea that there's a geometry consistent with multiple lines parallel to a given line through a given point, what we now call hyperbolic geometry. And they even proved some theorems for hyperbolic geometry, but they both stopped short of being able to get hyperbolic geometry because they just really couldn't put their mind around the fact that there might be such a geometry. Their imagination just fell short there, even though they were really close. Legendre, from 1755 to 1833 is his lifespan. He also spent a great deal of time on this problem. These are great mathematicians, okay? And some of the mathematicians who attempted these proofs actually even thought they had succeeded in proving Euclid's fifth process as a proposition, but they're always tacitly accepting something else as a postulate. Along the way, mathematicians were able to prove that the following are congruent, and then this is Euclid's fifth postulate that we just talked about, and the Euclidean parallel postulate. And some other things they turned out to be equivalent to it as well. The sum of the measures of the interior angle of a triangle is a constant. Turns out if that's true, then the parallel postulate must happen, and we're in Euclidean geometry. And then from that you can prove if sum of the interior angles of a triangle is constant, it actually has to be pi radians or 180 degrees. So that's another equivalent thing, that sum of the measures of the interior angles of a triangle is equal to twice the measure of a right angle. In other words, pi radians are 180 degrees. And that is that's the Euclidean angle measure postulate. Proposition. Once we actually accept the Euclidean parallel postulate as a postulate, then we'll be able to actually prove that as a theorem. But it turns out you could do it the other way around. If you took that as a postulate, this angle sum thing as a postulate, then you could end up proving the parallel. I guess it would be a parallel proposition or a parallel theorem instead of a postulate then. Another thing that's equivalent to it is for each triangle, there's a similar triangle of arbitrary magnitude. So we're going to study similar triangles in a couple of playlists or a couple chapters down the road. And there's other logically equivalent statements could be added to the list. So the best the mathematicians could ultimately do is replace Euclid's fifth postulate with some other postulate which is logically equivalent. Taxicab geometry was really not on the radar at that time. And we've seen that we can eliminate it with the inclusion of SAS postulate. Spherical geometry was also not acceptable since it could be eliminated from the beginning by the postulate that 2 points determine a line and the idea that lines extend indefinitely. And we've worked hard to write our postulates in such a way that keeps spherical geometry in our unified geometry study right up to the point we exclude it by accepting the Euclidean parallel postulate. However, no matter what, until we adopt the Euclidean parallel postulate, hyperbolic geometry is just as legitimate geometry satisfying the earlier postulates of Euclidean geometry as is Euclidean geometry itself. However, this is a hindsight from the development from these ideas. Finally, in the early 19th century, a trio of outstanding geometers independently and approximately at the same time were able to make that logical leap of imagining a different geometry where there were multiple parallels to a given line through a given point. In other words, hyperbolic geometry. Carl Gauss, one of the greatest mathematicians of all time, who lived from 1777 to 1855. Janos Bolyai from 1802 to 1860 was his uh, lifespan, and Nikolai Lobachevsky, who lived from 1792 to 1857, they all made essentially the same discovery in this period of time from about 1817 to 1829. We now know that by 1817, Gauss was convinced that the parallel postulate was independent of the other postulates, so that there must be a consistent geometry where Euclid's parallel postulate was false. Today we know this is hyperbolic geometry. And Gauss disliked controversy and did not publish his findings because he thought the discovery of a non-Euclidean geometry would cause a great deal of controversy. And actually, he was right about that. Gauss discussed his ideas about parallel lines with his mathematician friend Farkas Bolyai, who had earlier made several false attempts to prove Euclid's parallel postulate. Farkas's son, Janos, also worked on the problem. In 1823, Janos wrote to his father indicating that he had developed a consistent non-Euclidean geometry where the Euclidean parallel postulate is false. 2 years later, in 1825, Janos Bolyai was the first to publish the existence of such a non-Euclidean geometry. Gauss expressed admiration for Janos's work in non-Euclidean geometry, but he told Janos that he had discovered all this earlier, but had not published his results. Gauss was a little bit arrogant in that respect. But this is likely true, but in no way diminishes the incredible breakthrough discoveries of Janos Bolyai, who probably did most of that work on his own. Meanwhile, Nikolai Lobachevsky independently published a work on non-Euclidean geometry in 1829. Now, neither Gauss nor Bolyai knew of this work since it was published in Russia in a somewhat obscure local journal, nor did Lobachevsky know of the work of Gauss and Bolyai. In 1840, Lobachevsky published a 61-page paper detailing his work on hyperbolic geometry, and this work developed several new theorems in this new geometry. Probably it was the most complete work on hyperbolic geometry up to that point. Well, as Gauss predicted, this new geometry was initially met with some resistance. Furthermore, there was nothing yet like the half-plane model that we've been using in this class, or any other model for that matter. So at first, the work of Gauss, Bolyai, and Lobachevsky was not appreciated. However, as later mathematicians were able to flesh out hyperbolic geometry and develop multiple models for it, the discovery of hyperbolic geometry turned out to revolutionize the way we look at not only geometry, but also all of mathematics. Some important later mathematicians that worked on geometry and non-Euclidean geometry were Bernard Riemann. You may know him from Riemann sums from calculus. He lived from 1826 to 1866. Eugenio Beltrami, who lived from 1835 to 1900. Henri Poincaré, who lived from 1854 to 1912, and Felix Klein, who lived from 1849 to 1925. They all made subsequent further advances in the study of hyperbolic geometry, including the developing multiple models for hyperbolic geometry, one of which is the half-plane model we've been using. Knowledge of these discoveries uh, was critical in the careful treatment of Euclidean geometry by later geometers such as David Hilbert, who was the most important geometer since Euclid, and he lived from 1862 to 1943, and Edwin Moyse from 1918 to 1999, who wrote a book called uh, Elementary Geometry from an Advanced Standpoint, which honestly I've used as one of my major sources for this book. Eugenio Beltrami wrote a paper in 1868 which produced the first model for a plane in hyperbolic geometry by embedding it in a 3D place on the surface of a revolution of a tracix revolved around its asymptote. And this shape here is called a pseudosphere. So there's a way to make a Euclidean, non-Euclidean geometry, hyperbolic geometry, fit on this pseudosphere. Later models include the Beltrami Poincaré half-plane model, that's the one we've been using, and a circular disk model. In the circular disk model, the points of the plane are the interior of the circle. The circle itself is the edge of the plane, very similar to the edge that we have on our half-plane model. And in this disk model, hyperbolic lines are arcs of Euclidean circles with endpoints on the circle, and they're perpendicular to the circle, or they have open diametric chords to the circle. So here's actually a activity that some Lee Stemkowski put together that has it's for doing hyperbolic geometry on the circular disk. So the circle itself is the edge, like points at infinity, like our edge is in half-plane model. Here's a line. These should be right angles right here and here, and they're arcs of circles. Here's a line here, and here are a whole bunch of lines that are parallel to that one. One of those lines is a diametric chord here. Open endpoints, of course, no points on the edge are there. There's an example of a circle. Point is the center of the circle. Here's a point on there. The center of the circle will be closer to the edge than it is to the Euclidean center of that circle, but it is a Euclidean circle. If you want to connect this model to our model, our hyperplane model, you do it with a transformation called a circle inversion. Bernard Riemann was a student of Gauss who also worked on geometry. He gave a treatment of spherical geometry in his doctoral dissertation, and this work helped establish different geometries on an equal footing with Euclidean geometry. Felix Klein was the one to really bring all this work to fully mature level. He treated multiple geometries as being equally worthy of study within Euclidean geometry. And after the work of Klein in the early years of the 20th century, the discoveries of non-Euclidean geometries had a tremendous effect on the development of mathematics. Ultimately, the discovery of hyperbolic geometry, in which Euclid's fifth postulate for Euclidean geometry is false, but the other postulate is true, proves that the parallel postulate is in fact independent of the other postulates, thus vindicating Euclid's inclusion of it as a postulate. The discovery of hyperbolic geometry has ultimately had a profound effect on all of mathematics. From that point on, a set of postulates no longer was thought as being an obvious description of the way the world is, but rather they were seen as an abstract set of statements establishing a mathematical environment in which to work. Most of this historical information was based in part on the Mac Tutor History of Mathematics and several math history books that I've read. But this is a really good source here. You can see the link to it there. It's put together at the in St Andrews in Scotland, and it is a fantastic source of historical information that's freely available online. They have biographies of many mathematicians and lots of articles about different mathematical things. And then I've also teach a history of mathematics course. There's a playlist for history of mathematics. So in this playlist here, the next couple of videos I'm going to drop in here are a couple from my math history course on the discovery of non-Euclidean geometry and more 19th century geometry. I'll also go ahead and drop in one of a short biography of David Hilbert. And in these notes, you can see some of the slides from that. Okay, so that gives you a brief history of the parallel postulate, and we talk about that a little bit in as it relates to our geometries. Parallel postulate turns out to be a critically important piece of studying geometry, and it's very important in the history of mathematics.